Hi, I'm going to present the working title, Surrogates for the Assessment of Robotic Manipulator Reliability. My name is Fabian Molina, and this work was done in cooperation with Professor Korohishi and Jacqueline Machida from the Federal University of Technology, Paraná. The robotic manipulators are subject to uncertainty. The main source of uncertainty is the clearances of the joints. These clearances are necessary for the relative motion between the links, and the calibration and the control strategies have been used to minimize the effect of these errors. And therefore, it is necessary to develop methods that quantify the effect of these errors. The present contribution presents a comparative study of several methods to assess the kinematic reliability of manipulators by using the probabilistic theory and the fuzzy approach. Our methodology first, we present a method to compute the total error in the n effector produced by the joint clearances. Then the uncertain parameters of the clearances are modeled as random variables and also as fuzzy variables. And then 4 methods are used to evaluate the reliability. First, we have 3 methods based on the probabilistic approach, the Monte Carlo simulation, the first order reliability method, FORM, the second order reliability method, SORM, and the fuzzy method. Here is the outline of my presentation. The methods will be evaluated in this manipulator, which is a 3 degrees of freedom manipulator with the 3 revolution joints. The DH parameters are present in this table, and in this figure is present the model of the joint clearances. Each clearance introduced 2 additional degrees of freedom, one displacement in the x-axis and another displacement in the y-axis, and the 3 joint clearances introduce 6 different degrees of freedom in the manipulator set in this vector, in the vector lambda. First, the method to propagate the error of the clearances. I'm mapping the joint clearances in the total error of the n effector, as presented in this expression. This expression is based in the M matrix, and the N matrix is a matrix that is based in the homogeneous transformation matrix that takes into account the homogeneous transformation between the frames of the manipulator, and the N matrix, which is a total orientation matrix, and delta E is the screw representation of the joint clearances. Then the uncertain parameters are modeled as random parameters, as a normal random parameters. Therefore, each parameter is defined by the mean and the standard deviation as presented in this expression. When omega is a normal stochastic process, and then the fuzzy parameters are modeled as a triangular fuzzy variables as presented in this figure. The kinematic reliability expresses a measure of the position error exceeds the maximum error limit as presented in figure 3. The operator C represents a measure of probability or a measure of possibility. The first method, we have the Monte Carlo simulation. Monte Carlo simulation. This method has 3 stages. In the first stages, the uncertain parameters are sampled. Then the kinematic error is computed for each random input. And finally, the probability of failure is estimated as the rate of the failure samples and the total number of samples. In this way, is estimated the probability of failure. Then the first order reliability method, the random variable, the random vector is transformed into a standard normal variable u, and the state limit function is linearized by using the Taylor series, only considering the linear term, and the probability, the reliability coefficient beta is estimated by solving this optimization problem. Finally, the probability of failure is estimated by considering the standard normal cumulative distribution as presented in this expression. Then, and the last probability method is the second order reliability method. In this method is considered the state limit function as a nonlinear model. Therefore, the first nonlinear term of the Taylor series of the state limit function is considered, and the probability of failure is estimated by using the expression of equation 6. Finally, the fuzzy method, the error is expressed as intervals weighted by the membership function as equation 7 presents. Therefore, the alpha f, which is the measure of the probability of failure, is estimated by using the me operator that represents the possibility the possibility of failure, and this estimation of this possibility of failure demands the evaluation of the membership function that is a value that is contained between 0 and 1. In this figure is presented the fuzzy error of the end effector, and we observe the 2 conditions, an acceptable condition and a failure condition when a maximum error, when the fuzzy error exceeds the maximum limit, max. And the alpha f, possibility of failure, is estimated by using this expression. And we can see that this expression demands the solution of the optimization problem of equation 10. When the numerical results, first, we have the parameters that define the random variables, the uncertain parameters of the joints. Then the fuzzy variables that define the parameters, fuzzy parameters of the joint clearances, and also the geometrical parameters of the manipulator with the length limits and the maximum limits for each of the 3 joints. In the first result, we have the estimation of the error by using the fuzzy method and the probabilistic method. In the fuzzy method, we observe the membership function of the error, pairs in blue by considering the solution, the alpha solution of the alpha optimization for all the values of the membership function. And in red dot, we observe a linear approximation of this membership function. And we observe that the results are quite similar. And then for the random error in the second figure, we observe the histogram of the error and the approximation of the function of density. And we observe that the results also have a great agreement. Then we evaluate the workspace of the manipulator in the X, Z plane and in the XY plane. And we are going to evaluate the reliability, the kinematic reliability for 11 different positions as present in these figures. In this table, we can observe the outputs obtained of the probability of failure by using the Monte Carlo simulation form and SORM terms. And we observe an agreement between these three methods. Nevertheless, in some positions, there are some differences, and we can observe that the SORM method correct the differences between the form and the Monte Carlo simulation. The Monte Carlo simulation is our baseline to evaluate the probability of failure, and we observe good results for both methods. Then the probability of failure is evaluated for the workspace, and we observe that the probability of failure increase in the outer border of the workspace. This is obtained because the manipulator is completely extended. And we observe a similar behavior by considering the fuzzy method as presented in this figure. Then we evaluate the computational complexity, and we observe an agreement between the two methods in the computational cost. As a conclusion, we observe that the methods, by using the probabilistic and fuzzy approaches, have good results. The kinematic reliability is a criterion that is used to evaluate the kinematic performance of the manipulator. And as a future work, we will use these methods for the optimal design of the manipulator. Finally, the acknowledgements for the sponsor, the MPQ and CAPES, and thank you for your attention.